Welcome to the Origin Science Scholars Program of the Institute for the Science of Origins. The Institute is a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream. The Fall 2014 Origin Science Scholars Lectures are presented with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. Tonight, we are pleased to be here at the Cleveland Museum of Natural History for Searching for Life in All the Cold Places with Dr. Thomas Orlando. Dr. Orlando is a professor in the School of Chemistry and Biochemistry and the School of Physics at Georgia Institute of Technology and a fellow of the American Physical Society and of the American Association for the Advancement of Science. Please join me in welcoming Dr. Orlando.
I would like to start out by thanking Dr. Starkman for the opportunity to be here and to participate in this very fascinating series. And also my friend and colleague, Clemens Berta, who's a faculty member here in the chemistry department at Case Western. So what I'm going to do is give you a little bit of an overview of searching for life in all the cold places. In particular, we're going to follow the mantra of follow the water. And I'll say a few things about water formation during the early stages of solar system formation, and then we'll follow the water till now. And then we're going to give some overview of recent discoveries in our solar system, and in particular the issue of water on the moon, and the idea of Europa and Titan being prototype planets for searching for clues about the chemical origins of life. I would like to point out that though I will be staying in our solar system for this particular talk, what I'm about to speak about is relevant to solar systems outside of ours and the search for extrasolar planets, which I know Professor Starkman has been active in. Now, I'll say a few words about the formation of planets. They were made by the accretion of small particles in the solar nebula. The solar nebula was a dust-filled cloud, and then these particles interacted with one another, and this is a clear case of the rich get richer, or the bigger get bigger. So there's collisional processes which occur, there's gravitational forces which cause these particles to agglomerate, and the collisions will continue, and you'll have these small particles become much bigger ones, and these large look like rocks. They're basically termed planetesimals. Planetesimals are little baby planets that continue to grow. This is a very dynamical situation with very complicated collisional processes, and over time, as these form, they will have orbits around the star and ultimately form a solar system of orbiting planets. Now, this is a very simple slide. I call it Planetary Science 101. It's plotting out the relative distance of the planets from the sun in our solar system. This is taken from the NASA website. Incidentally, most of the really pretty pictures that are of these planets have been obtained from the NASA websites. And you can see here the closest planet to the sun is Mercury, then we go over to Venus, and then Earth is over here, and then there's this number here, 1. 1 is the term that 1 AU. AU is an astronomical unit. It's roughly 93 million miles, or 150 million kilometers. And so they're normalized relative to the distance from the sun, and then we move on to Mars, and then we have the giant planets, Jupiter, Saturn, Uranus, Neptune. And I think people might argue that I have a mistake on the slide here. I've included Pluto. Okay, I believe Pluto was mistreated and they were kicked out of the planetary club unjustifiably, okay? And so there might be a resurgence to bring Pluto back into the fold, okay? All right, so Pluto's hanging out there. One thing that's really important is as we look at the distance from the sun, obviously one thing that changes dramatically is the temperature. And so this is where we're going to talk about cold places. And in particular, we're going to kind of try to zero in on this blue line here, which is the so-called habitable zone. So if you look at Venus, then you move on over here, and there's this blue line here, and then Earth is here. This blue line more or less represents where you can have liquid water. Then we get over a little bit colder and it's starting to form ice. Actually, I looked at this, and I grew up in Rochester, New York. And so this is sort of the edge of the habitable zone, right? It's you might call it the lake effect line, right? And I think people here in Cleveland might understand that as well, okay? This might be the lake effect line here, and then we move over, which is barely the habitable zone, and then we move on out to much colder environments, to Jupiter and Saturn. A word on the actual temperatures that are correlated with these distances. Up here on Earth, this on the left-hand scale here, this is the temperature in degrees Kelvin. This is the distance in logarithmic scale in AU. So we normalize here, 1 AU is Earth, then we move on down to Mars. We're down to about 225 Kelvin. And then we move a little bit further out, and here is this ice line. This is at 150 Kelvin. This is where water freezes out rather rapidly to primarily amorphous ice. And then if I keep going further out towards Jupiter, I get to a temperature where I can start to freeze out CO2 and make CO2 ices. And I can be even further out to the area where Pluto is, and KBO is the Kuiper Belt objects and comets. And you can start to freeze out methane and nitrogen. So these are then solid ices at these relevant temperatures. I'm going to talk about things that are happening on the moon of Earth and point out that the tilt axis of the moon is such that there's the poles of the moon and permanently shadowed regions of the moon that have temperatures that are below 100 Kelvin. So they're very, very cold. And then we're going to look at moons of Jupiter and Saturn whose temperatures are about the same. Now, before I do that, I want to give a sort of a atmospheric chemistry perspective on what are molecular signatures for life. And these molecular signatures for life are also pursued by people who are searching for exoplanets. And in particular, you would look in the atmosphere and you look for spectroscopic signatures of the presence of molecules such as O2, carbon monoxide, and carbon dioxide, and methane. Typically, you need to have all four of these present to have a credible scenario for life. If you look over to the right, a true positive would be all of these present. And in particular, not only do you have O2, but you have ozone, which is an oxygen atom that's reacted with O2 to make O3. There's another thing that's pretty clear in this picture, and that is that you need to have, from our perspective, liquid water. And so you have this very nice green landscape here with liquid water, and then in the atmosphere we have a significant amount of water vapor. So water is a critical component of life, for the search for life in other environments. In addition to water, we'll like to see oxygen and ozone and methane. So these are sort of the molecular signatures that you would be looking for spectroscopically. There's also physical signatures for the possibility of life, and then I alluded to that, and that is the presence of liquid water, or in particular, the presence of liquid or salty oceans. Okay, and if you look at our beautiful planet here, it's a water world. That's no surprise to any of us. And so we are very focused on looking for Earth-like oceans elsewhere. Now, another thing that is pretty important and something that we cannot overlook is in order for life to be sustained, we need to be protected from radiation. So we need to have a radiation protection element as well as an environment that could sustain the production and multiplication and persistence of biologically important molecules. Now, I mentioned very clearly that we need to understand whether or not another environment has an ocean. And believe it or not, the source of our oceans remains a matter of controversy. So we don't fully understand what gave rise to the oceans on Earth. And so it's going to be a little bit difficult to fully understand what gave rise to oceans elsewhere. But there are some strong and incredible scenarios for this, which is cometary delivery during the post-Hadean late heavy bombardment period. So a significant fraction of the water was delivered to Earth by comets. Now, if you look in the literature and you see much of the work that's being done on comets when they analyze these, and they analyze the coma and the tails, they're observing a significant fraction of molecules that are not just water. Actually, there's a significant fraction of organic material in many comets. And in fact, I would encourage you to think of comets as not just big ice balls, but icy dirt balls. They're more dirt than ice in many respects. The dirt being organic material and non-water ice materials. So that's one way, this cometary delivery by bombardment. This goes back to the very first slide where you can have surface adsorption on condensing grains. And these grains are the ones that are agglomerating and being involved in accretion that would lead to the formation of the planetesimals. So you can have surface adsorption on the grains. In addition to surface adsorption, you can have water-like groups on the grains. And the water-like groups will be hydroxyl groups. Water is H2O, and a hydroxyl group is OH. Okay? And so you can have these grains persist, and they can be sort of forming planetesimals that when they're heated, they actually release water, and so the water is formed within, and it's formed during the planetary formation process itself. There is some evidence for that. If you look at some of the grains that have been captured, there's these water occlusions, these hydrated water inclusions within these grains, right? So there's evidence that sort of supports this grain-mediated source term. And one thing that I want to come back to is I said that the accretion phase is very dynamical, and there's a lot of mixing of the grains. And so you could argue that there were dry inner grains, but they were colliding with wet outer planetesimals during the settling and formation. So there are two primary scenarios. One is that the water was formed during the planetary formation process, and the other one is it formed later by cometary bombardment. But the jury is still out on this particular topic. So our water world. More than 70% of Earth's surface is covered by water. And there are several theories regarding the ocean's origin. But the bottom line is we like and we need water. I actually like water a lot, and in fact, I surfed quite often. I'm not in shape to surf anymore, and I never really surf waves this large. This is not me. Okay. You can also tell by the hair here, it's a little bit less, but a really good stance here. So anyway, he's surfing significant waves, and we need water. Right? This is no surprise to everyone. I actually like this particular photo. They're not my children. My children are a little bit older now. So we need water. Okay, so now we need water, and I also mentioned that if we're going to look for life elsewhere, we need to make sure that we have some protection from radiation. So if we look at the sun is our friend and our foe. The sun is clearly the fuel source for Earth. It's our energy source, and we need to have an energy source for metabolic processes. But we have to pay close attention to the fact that the sun also emits radiation that can destroy the atmosphere and the surfaces and most life on Earth. Now, luckily, we are shielded from harmful radiation. What's not clear from this picture, if you look in this aurora here, the sun is always emanating what is called the solar wind. And the solar wind is a neutral plasma with significant densities of protons and electrons that are moving together, and the proton energies and electron energies are around half a keV to 1 keV. keV is kilo-electron volts. You see this thing up here, this is a coronal ejection event, and so when this happens, there's a sporadic release of a lot more energetic particles than what this normal solar wind is giving. Now, we have to realize that Earth is kind to us in the sense that it has a magnetic core, and we therefore have what is called a magnetosphere. And the magnetosphere is what's protecting us from radiation. So over here, we have the solar wind coming, and it's deflected, and you have this bog shock, and then the magnetopause, And then right in this little spot here is the Earth. And you can see right around here, there's these deflection lobes, and then there's these tails that are back here. These are the magnetic field lines that are emanating from Earth. And the particles are actually deflected primarily by these magnetic field lines. So the radiation that would be hitting us from the solar wind is primarily deflected, except for in the poles here, because you can see these magnetic flux lines go towards the pole in the north and towards the south. Okay, and so that is actually what gives rise to the beautiful aurora borealis in the north, which is the northern light shows, where you have energetic particles coming in, and they're ionizing and exciting the molecules within the atmosphere, and they're emitting radiation that we can sort of measure and monitor. And they give rise to very beautiful shows. A very similar thing is happening in the southern hemisphere, and this gives rise to the beautiful aurora australis.
Okay, do we know what happened to the projection when the Earth has periodically changed magnetic poles?
So that's an interesting question. So there's, so the sun has a sun cycle, and that periodically changes its poles. And then you have the magnetic field lines that cross, and you have entry points for energetic particles during that switching time, and that, in many people's minds, have large effects on the atmospheric chemistry and large radiation fluxes that are correlated with those solar cycles.
I was wondering about the origin of comets. If that's one of the theories on how we receive so much water, are the comets out in the Oort section, the Oort cloud, way far out, or where the heck do they come from? Way far away, or where?
Yeah, okay. So a lot of the comets are coming from the Oort cloud, and they have long period comets and short period comets, and they're making its way into the inner solar system. If you go back to the very first slide during the formation of planetesimals, if you look at the sort of the nature of the nebula, then there's a cold region, and if you go out beyond, say, 10 to 100 AU, then there's an icy region in the midplane, and they're presumably formed in these icy regions during the mixing. And then they can be involved in the formation of planets, but basically a lot of the comets are fairly small, and they're scattered by the larger planets that are being formed. And then they do come in, though, and they have this recurrence from the Oort cloud primarily, where they can collide.
The atmosphere of Mars, have you heard any data back from that?
Personally, no. I am involved in some Mars work, but it's not on the atmosphere. It's looking at some of the rocks that they will be collecting and trying to see if there's biosignatures and molecules in the minerals. But no, so I'm not familiar with the atmospheric measurements.
Thank you for joining us. You've been watching Dr. Thomas Orlando of Georgia Institute of Technology discussing the importance of water to life, and therefore to the search for life on other planets. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at www.case.edu/origins. In the next part of the talk, Dr. Orlando will discuss solar system history as it relates to the habitability of moons and planets. Now, back to the talk.
So now I'm going to move on a little bit and say a little bit about the moon, because I mentioned it already, but I have a question to ask you. Is the moon shielded by our magnetosphere? Okay, so we have some people who know. Yeah, so it's not. It's outside the magnetosphere. So here's a cartoon of our magnetosphere. It's not this one-dimensional slice. It's, of course, the three-dimensional slice, but the moon spends most of its time outside the magnetosphere. So that means the moon is basically irradiated significantly and bombarded with protons and electrons from the solar wind. So we have to pay attention to that. And there's a lot of people in the planetary science community in particular who think that the water could be produced on the moon by solar wind bombardment, which is a proton coming in. It's a H+, and it can be neutralized, and it's a hydrogen atom, and then the hydrogen atoms can interact and react with water to form OH groups, and then react with silicates to form OH groups, and then form water. Part of that has to do with a lot of observations that have been published over the past couple of years, where they mapped out the optical signatures of what is purported to be water on the moon. And there is a clear interest in water on the moon because there's continued discussion of going to the moon, and if so, then water is an absolutely necessary resource. I'm not saying we're going to colonize the moon. I'm just saying that if water is there, it's a very important resource. Now, if you looked at the map of the moon from that science article, what it was a distribution spatially of the reflection measurements that were carried out primarily by M-cubed, which is the moon mineralogy mapper. And so that's a spectrometer that's aboard a spacecraft, and what it's doing is it's looking at the reflected sunlight from the lunar surface. It goes into the spectrometer, and then the spectrometer then disperses the light and, from blue to the near infrared, and then you can sort of sit on a particular wavelength and then look at that wavelength intensity or lack of intensity as a function of a position or pointing position on the moon surface. So this way you can map out a spectroscopic signature of water or OH groups on the moon with pretty good spatial resolution. So there's a series of papers in this science issue, and all of them presented very compelling evidence for the presence of, I put down the word hydroxyl, which is OH, excuse me, and water on the moon. Some of the compelling evidence is here. This is the output of the spacecraft. So this is measurement of the reflection of the reflected light over this wavelength region here from 2,800 nanometers to 3,600 nanometers. So this is very red, infrared. And when it goes down, it means it's being absorbed. The light is being absorbed. It's not being reflected. And you can see that it starts going down somewhere around 2,800 nanometers here. The plot here on the right is the reflection spectra of ice, and then the reflection spectra of water, and reflection spectra of minerals that have been interacting with water, but what's on the mineral is a hydroxyl group, so that's just OH. And there's a problem with the spacecraft data in the sense that it only looks at half of the band. So it only looks where it goes down, it doesn't look where it comes up. So that's a technical limitation of the instrument aboard the spacecraft. They've now redesigned these so that you can look at the full band profile. But now what's mapped here is sort of the intensity of this line here, right here, as a function of position on the moon. Okay, this is a little bit easier to understand. This is the reflection spectra of the moon on water versus the reflection spectra of water on the moon. I actually like this photograph here, and it's easier to understand. Okay, so, but we've spent a lot of time thinking about this, and we've done some measurements, and I won't go into the details, and we've done some modeling, and we predicted the distribution of hydrated minerals, which is the presence of OH, not the presence of water, but the presence of OH, and compared that to the remote sensing data from the Galileo, or from the NIMS M-cubed spacecraft data. And what we can do is a reasonably good match. It's hard to see because of the color coding, but what we've done is we've mapped out where the OH intensities are relative to the equator of the moon and the poles, and we can map out and match the spacecraft data reasonably well with a fairly simple model. The trouble is that it's not water, okay, it's OH, right? So our work is implying that a lot of the spacecraft data is looking at the falling edge of the band, which is primarily hydroxyl groups. It is not saying water is not on the moon. We're saying that in the equatorial regions in particular, where the solar flux is high, where the proton bombardment flux is high, the predominant channel there is formation of hydroxylated minerals. And you can explain a lot of the reflectance spectra this way. Now, I said we did modeling. We actually did some measurements. We build lots of equipment. We are at Georgia Institute of Technology, and so there is a big technology component to our program, and we build these ultra-high vacuum chambers. The pressure in this chamber is 10 to the minus 10 torr, and then we have mass-selected ion beams. We can come in with a proton beam of roughly the same energy. We can come in with electron beams of roughly the right energy. And we can come in with other particles, Lima alpha photons, and irradiate lunar material. And the hardest part about this whole experiment, by the way, was getting approval to get lunar material, okay? Not building the machine. The machine was actually pretty straightforward. But now NASA has approved us, and we are formerly the Southeast Center for Lunar Science. My students call us the Southeast Lunatic Center, which is probably more accurate, to be honest. And they like to bombard lunar material with protons. And so when you do that and you analyze the data, we have a fairly simple model. There are no equations. I promised Glenn there would be no equations in this particular talk. I also promised him, and it's not, and I didn't hold completely true to my promise. He asked me to keep the red out, right, because of some technical issues with regard to the red coloring in the words. So I was able to keep out most of the red. But as we move to a Europa, you will see that I was not able to keep the red out completely. All right, so anyway, here's our model, and it's the proton coming in, H+. It interacts and strikes the surface, which is primarily a silicate. The proton forms a hydroxyl group, preferably near a defect, which a defect in this case for us is simply an oxygen atom missing from the mineral. And then it reacts, and then you can form this hydroxyl. And over time, and the flux is reasonable, you can get a hydroxyl density where all of these oxygen atoms that are next to a vacancy are hydrogen terminated. Okay, and then at a certain temperatures, these hydrogens sort of like to interact with one another. They interact with one another. And instead of one coming off of here and forming water, it's a lot more favorable energetically for them to just form hydrogen. And then hydrogen gas leaves. So H2 is what's actually coming from the surface. So one of the primary effects of protons irradiating the surface is hydroxylation, formation and release of H2, not water. So water in our model is not formed. Okay, so some people still think water could be produced on the moon by the solar wind, and that's fine. We don't. We actually believe that the proton interaction with the silicate makes hydrogen. And there's plenty of hydrogen that's actually backscattered off of the moon. And so, but it doesn't say that there isn't water on the moon. There's plenty of water in the poles. And there's plenty of water in what are called permanently shadowed regions, these pieces where you basically have the solar photon flux shielded so that it never gets warm. And in these permanently shadowed regions and in the poles, there's absolutely plenty of water. If it's below 100 degrees Kelvin, which these are, the water will hit and stick. And it'll stay there for a very, very long time. And the poles don't see any solar flux. So once it's there to stay.
By using technology, would it be possible to turn the hydroxyls into water on the moon? I've heard from an astronaut that some lunar material are up to 1/3 oxygen.
Right, so there's a big push for that. Particularly if you look at this, if you do want to have colonization of the moon, or if you want to have a resource there, that's a very good path, and try to do this. It takes energy and it takes a fair amount of temperature to do this. Now, one thing that I didn't say this. The temperature at which we're doing our model is the temperature excursion that the moon has, particularly at the equatorial region. Okay, so that doesn't get very warm. It can get up to 400 degrees Kelvin. And that's not that hot. And it turns out, this is an interesting question. It turns out that we've done the same model for Mercury. Assuming that Mercury's regolith or surface is similar to the moon. If you get to 600 degrees Kelvin or higher, you do make water. And so our model actually says that Mercury is loaded with water on the poles. And so that happens, but you have to go to a much higher temperature than the moon is actually going over during a natural progression or natural lunar day. And the issue with Mercury is interesting because this is happening at 600 or 700 degrees Kelvin. And then the water's formed, and it desorbs. It leaves the surface. But it doesn't have an escape velocity, so it comes back. It might bounce around and break up, or it may reform, and then this does this hopping thing for a long time. Eventually, it gets to the poles, and it sticks. And so water is on the poles of Mercury, and there's no question about it. And the the solar wind may very well be part of that source term. And that sounds very strange, right? Because Mercury is like right up against the sun, and so how could this ever support water? Well, it turns out, and I'm not sure of the reason for this, but the tilt axis of Mercury is exactly the same as the tilt axis of the moon. And so there, the moons or the poles of Mercury are also permanently shadowed, or they never see a flux from the sun.
So what does that say about Venus?
The Venus has, and so one of the reasons why it works for Mercury and it works for the moon is they're airless bodies. They have essentially no atmosphere. And so a lot of the radiation just comes rattling in and interacts directly with the surface. If I have other planets that have atmospheres, then the atmosphere absorbs a lot of the radiation. And I haven't thought very much about Venus, mostly because it's got a complicated atmosphere. But so I would think that it would not necessarily be happening on Venus because the solar wind component of it is not irradiating the surface quite as much. The other thing about Mercury, and I neglected to mention it, it has a magnetosphere. It's a pretty wimpy magnetosphere. But it does allow sizable fluxes of energetic particles to go down and interact with its surface.
I hope you've been enjoying the Origin Science Scholars Program with Dr. Thomas Orlando of Georgia Tech. Dr. Orlando is a fellow of the American Physical Society and the American Association for the Advancement of Science. In the second part of our talk, we learned about the history of the solar system and how it relates to life on the Earth and elsewhere. In our final segment, Dr. Orlando will look in particular at Europa and Titan as candidate environments for life. Now, back to our talk.
Now I'm going to move further out to looking at other moons that we don't typically think about. This would be Europa here. This is our moon. And then I want to look at this big moon here, which is Titan. So Europa is one of the Jovian satellites. It's in the Jupiter system, and then Titan is in the Saturnian system. And some of the interest in this is related to the purported observations of these particular moons supporting an ocean. In addition, Europa has been, oxygen has been observed on Europa and within the exosphere of Europa. The very first report of the Jovian or the Galilean satellites is from Galileo, okay, in the Starry Messenger, Sidereus Nuncius. Actually, this is interesting, and Medicia Sidera is the funding agency. This is the family who funded Galileo to do this. And so even back then, you have to pay homage to the funding agencies, quite rightly so. Okay, and so this was his first report of them, and this is taken as a translation of what he had written in the Starry Messenger. He was looking at Jupiter, and he was mapping out what he thought were stars around Jupiter, and then he noticed that these were coming into place and out of place, and was looking at them, and he noticed that these stars were orbiting Jupiter. And then he plotted these different orbits and these different observations as a function of time. And then he writes, I therefore concluded and decided unhastily that there are these stars in the heavens moving about Jupiter. As Venus and Mercury revolve around the sun, which at length was established as clear as daylight, numerous and subsequent observations, Galileo. So these so-called stars were the Galilean satellites. They're the moons of Jupiter that he was able to observe with the telescope that he made back in quite a while ago. So here's a more sort of up-to-date picture of the revolving moons around Jupiter. These are the Galilean satellites. And make note of this as we discussed the fact that Earth has a magnetosphere. The Jovian Jupiter has a pretty big magnetosphere. So these are the magnetic flux lines that are emanating from Jupiter. And then they're trained in this, you can see this red donut here. There's this ion torus. It's a very, very complicated plasma. Actually, it's a synchrotron. It's one of the few that DOE didn't pay for, okay? It's a synchrotron facility here. And there's a lot of energetic collisions that are occurring with the moons that are sort of embedded in this plasma torus. Okay, the moons that we'll be talking about are the one in particular is Europa. And as I mentioned, there's a purported subsurface ocean beneath the icy crust of Europa. And these are tidally locked to Jupiter. And as they rotate around, you'll see that there's a sort of trailing edge and a leading edge relative to the plasma. So the plasma is sort of always hitting it sort of in the backside. And then the front side is going into the plasma. So the question is, what's up with this subsurface ocean? And what does this plasma do to the Europa surface due to the radiation bombardment? So let me say a little bit about the first part, the radiation bombardment part. Jupiter's enormous magnetic fields channel electrons down onto the surface. There is no atmosphere there, so there's no stopping of these particles onto the surface. They're following these flux lines here. And so you can see them that they can get channeled onto the poles with very high fluxes. And they can also, you'll have the ions following the field lines. And so you have ions that are within the plasma. So not only do we have electrons, but we have ions. And not only do we have protons, we have oxygen ions and sulfur ions. These are coming from the other moons, in particular Io, which is spewing out sulfur. And these energetic ions are also hitting the surface. There are spectroscopic observations of the presence of O2, molecular oxygen, on Europa and in its atmosphere. And so the question is, how is that produced? And is that a signature of any kind of biological activity? Because O2 is one of the main molecules you would look for in addition to water as one of the molecular signatures for potential life elsewhere. And this may harbor a subsurface ocean. So there are some experiments we did, and we asked what O2 looks like on Europa, and it looks like this, O2. Looks pretty much the same as what you think it looks like, okay? And say we took an electron beam, simulating these particles following the field lines hitting the surface of ice, and then we wrote it, and we moved the beam around, and we wrote O2. Then a little while later, we took the same beam, and we rastered it across like a TV camera, and we looked at the molecular oxygen that came off as a function of the position of the electron beam. And what you find is the O2 molecules are only coming off where you did the first step. So there's two things that have to happen before you can form O2. And all the O2 is made by radiation. This is a total aside, but I did this when I was up in the Northwest. And somebody asked me, how long did this take? So I had a new unit here, actually. This was on the order of 2 Starbucks. And that's true. It took us two Starbucks later. Okay, then we did this here. Each one was about a Starbucks. So roughly an hour and a half, which is a lot of coffee, by the way. So anyway. Okay, so O2 is formed by radiation. And so we had this paper in Nature where we discussed the mechanisms for doing that. And a lot of people thought it was an oxygen atom running around, another oxygen atom running around. They find each other, they like each other, they shake hands and leave as a happy molecular O2. That's not the case. Actually, the first step makes a precursor, it makes sort of a peroxide, and then another electron comes and makes the O2. So the mechanism is not so important. Actually, for the purposes of this talk, what it says is O2 is made by electron impact from the radiation. So all the O2 that is produced is from radiation. It is not a sign of life. It is not a signature of life on Europa. The presence of O2 should not be considered that. However, we did say that it may have an ocean. And so let's look at that. Does Europa have an ocean? Well, you look at this, there's these color enhanced, this is where I couldn't get the red out. These color enhanced figures here where you can see this non-white material here. It's called the non-ice material. And the question is, what is it? And if you took a close look at this, you also see that there's geological features that look like icebergs that have broken. So there's a so-called Europa ocean puzzle, and you can rearrange these, and the geophysicists have rearranged these, and they looked at how the tidal forces between Jupiter and itself gives rise to this tidal heating and compression, and they can reconstruct some of this as a fractionation of the ice. So this is a geological fractionation of ice. In order for this to happen, though, in their models, they say that there's a subsurface ocean. Okay, so there's compelling geological evidence for a subsurface ocean. There's also compelling optical measurements or spectroscopic information with regard to the presence of a subsurface ocean. This is data from the near-infrared mapping spectrometer. So this mapping spectrometer is essentially the same as the one for M-Cube, where they were looking at the infrared features of water. And what they did is they looked in these red zones, the linea, and they looked at what the optical signature was, and they compared it to ice. And these are very perturbed bands relative to ice. This is not a very good, it's much easier to see in color. Sorry about that. So these sharp ones are ice, and the broader bands here and here are the non-ice material. And a lot of scientists have interpreted this non-ice material as the signature of the presence of minerals on the surface of Europa. In particular, these types of minerals. So they're simple minerals. They're actually salts that are known to form during the dissolution of a primitive ocean. And you can see the red line here is the NIMS spacecraft data of these linea, or this really dark red region here. And you can see if you look at this thing called natron, which is sodium sulfate, you can see the band features are more reminiscent of that than montmorillonite or these other more standard clays. So the interpretation of this work is that this red material is indicative of there being minerals that are plated out on the surface, and the minerals are primarily salts that could be from a primitive subsurface ocean. It's hard to see this here, but there's this inflection here, and Tom McCord is a friend of mine, and I always tease him about this. He can't fit this. The plot is not finished here. You can't fit this because he says there needs to be a yellow coloring agent. Yellow coloring agent. Well, you know, organic molecules absorb light in the yellow region, and there could be a yellow coloring agent. So, you know, the question is, what might that be? Here's an overview of an artist's rendition of how you might get these minerals or yellow coloring agent on the surface here. So you start out with having a icy crust, and then beneath that is an ocean that may have hydrothermal activity under there. You have to have some heating to melt the ice, and so the theories for heating, the primary theory for heating is the one I already mentioned, is that there's tidal heating between Europa and the gravitational interaction with Jupiter. But you can have these things called cryovolcanism events and geysers. They have not been observed on Europa directly. Geysers have been observed in Enceladus, which is one of the moons of Saturn. Okay, so let's look at this a little bit more. The particular core here is an icy crust with a solid ice, where the theories of the tidal heating and the tidal fluxing is more reminiscent of this, which is similar to the artist rendition, where I have this icy crust, I have a subsurface ocean underneath here, and then I have fractured zones here where this material can then end up on the surface via cryovolcanisms or geysers. And if you look at that, and you look at the minerals that were purported to be there, they were salts. So this is sort of like a primitive salty ocean that may be getting onto the surface of the ice that then is spectroscopically mapped with the spectrometer. Okay, I mentioned this yellow coloring agent, and so I did some deep thinking on this. And I'm going to zero in on a zone here and ask what the yellow coloring agent is. And I became aware of the fact that this is a yellow coloring agent which is everywhere on Earth. You can't go anywhere on Earth and not see this yellow coloring agent. Anybody want to guess what it is? Sulfur? No, it's McDonald's. Okay. Actually, it is sulfur, but anyway, it's sulfur. So I just thought, McDonald's is now evaded. It's on Europa now, right? And there you go. Okay. So just a few minutes of a talk on a little bit on Titan, because there's a significant amount of organic material on Titan. In fact, it's covered with lakes of organics. And so Titan is Saturn's largest moon. It's the only one with a very thick methane-rich nitrogen atmosphere, so the atmospheric chemistry here is very, very complicated. It makes this very complicated organic haze. It looks yellowish orange, and this haze then sort of precipitates down onto the surface. And the Huygens probe has sampled a lot of this as part of the Cassini mission. And there's a very interesting results that are coming from that, and there's a lot of people who are interested in Titan as a sort of a prebiotic chemical system within our solar system that can give us clues with regard to some of the complicated organic chemistry that may be occurring as precursors to the formation of more complex molecules. Titan's surface is not a fun place. I mean, it's still pretty cold, 95 Kelvin or so. The density is twice that of water ice, so there's a significant number, there's a significant amount of rock that's intermixed with the ice. And a lot of this ice is not water ice. It turns out it's organic material primarily. Now, it's not to say that there isn't any water ice, but that's probably subsurface according to the models. One thing that they have seen, and it's a remarkable image here, that Titan has a lot of lakes and rivers. There's a lot of discussion about water on Mars and the geological features that look like there's a liquid water on Mars. Well, there is for sure liquid on Titan. It turns out, though, that it's not water. And before the Huygens probe, most of the planetary scientists thought these rivers and lakes were condensed methane, based on the density of methane that was in the atmosphere. But actually, it turns out that it's probably ethane. So there's lakes of ethane condensed out on the surface of Titan. So there's a very complicated mixture of minerals and organics and liquid organics. So if there's chemistry that's occurring on the surface of Titan that's reminiscent of the formation of polymers that can carry function, they're not going to be the polymers that we're used to, like RNA and DNA, because we don't have the oxygen present, we don't have the sugars, and so we would have a very different protopolymer that could serve the same function as RNA and DNA, but it's not the same. Okay, there is a growing body of evidence that there is a melt zone, which is termed an ocean within Titan, and it's probably a little bit lower down, so that the surface is primarily organic. Then there's this icy shell, and then a melt zone here, and then another icy shell. But this is the important thing here, is that they do believe that there's an ocean on Titan as well. And so therefore, it is another destination with an ocean, and therefore there's quite a bit of interest in sort of going back there to gain more information by either landing or having a penetrator go in and see if they can find an ocean. This mission hasn't been sanctioned, whereas a mission back to Europa has been sanctioned from NASA's perspective. And on that, I'm going to finish up with a sort of a general philosophy slide in some respects from the point of view of a chemist. If Titan were to harbor life, it may be weird life. Titan remains an interesting place to look for clues of how complex molecules formed, and it's an interesting journey in chemical evolution. And so this is a chemical evolution to form DNA and RNA complexes that contain sugars and phosphates and complicated arrangements, it's nothing to say that you can't have some organic chemistry occurring that can have complicated replications that could serve to carry information. And so Titan is also considered an interesting point for a journey in chemical evolution. And on that, I'm going to open it up for further questions.
This lecture is part of the Origins Science Scholars Program of the Institute for the Science of Origins. The Institute is a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream. The Fall 2014 Origins Science Scholars Lectures are presented with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origins Science Scholars Program, including a full video archive, please visit the Institute's website at www.case.edu/origins.